Okay, I am going to try my best to get this done all in one shot. So if I mess up, I'm just going to keep on going. So just as a quick review, since it's been a while, these are the ionic bonding notes that we took earlier during our bonding unit. And the one thing focus on for this next part is this part right here. Okay, ionic bonds and ions conduct electricity when they're dissolved in water. Okay, now how do they dissolve in water? That is what we're going to get to right now, which is going to lead to acids and bases. So I'm reviewing all of this so that the next part of the acid-base unit hopefully makes more sense. Since I'm not in my classroom, this is going to be kind of tough. So, water is polar, right? So I'm going to draw my water molecules, and if you want to add this to the notes that you've already taken for this section, for section 4, that would be a good idea, just so you have it later on for a reference. Okay, so here's my water molecule, and if you remember, the oxygen side of the water molecule is negatively charged and the hydrogen side is positively charged, and that's because, just again for review, oxygen's got 8 protons, hydrogen each has 1. So if oxygen and hydrogen were to play tug of war with the electrons, the oxygen would win. And since electrons are negatively charged, the electrons spend more time around the oxygen atom, which makes the oxygen side of the water molecule negatively charged, okay, and the hydrogen side positively charged. So I'm going to erase this for now. Okay, now what does that have to do with ions? This is what it has to do with ions. Let's say we have NaCl, which is an ionic compound, which is table salt. Right, so what happens when you dissolve salt in water? The ions break apart, and you end up with a Na1+, and I'll just put plus, and a Cl-. So you end up with the ions breaking apart, and the reason why they break apart is because the water works its way in between the two ions, and the sodium, which is positively charged, attaches to the negative side of the water, and the chlorine, which is negatively charged, attracts to the positive side. And that's why salt dissolves in water. Okay, I hope that makes sense. What's really happening is the water is going between the two ions, so that you have the sodium, which is positively charged. You can look on your periodic table for this. Sodium is positively charged, hooks on that. Chlorine, negatively charged, hooks onto the positive. And that's why salt dissolves in water. So that has to do with solubility. How well does salt dissolve in water? In baking soda, I use the the aspirin as a way to dissolve, show solubility. Okay, so how do things dissolve in water? This is how it works. Okay, now salt is really good at dissolving. Water is really good at dissolving stuff. Okay, so in your notes, I'm going to erase this. Okay, so here we go. This is what makes an acid. If you have HCl, okay, so I'm going to draw my water molecule again. Okay, this side's positive, this side's negative. Okay, you can think of H as like an ionic compound, just like salt. So the way that HCl is going to dissolve in water is it's going to dissociate And that's what it means by, it means breaking apart, to a hydrogen ion and a chlorine ion. Okay, so the chlorine ion, just like with salt, attaches to the negative side of the water, and the H attaches to the positive side. If you have, and this is the whole point, if you have a positive hydrogen ion dissolved in water, that is an acid. Okay, so anytime you have a hydrogen ion dissolved in water, it's called an acid. And I mean, that's it. That's it. The more hydrogen ions you have dissolved in the water, the lower the pH, or the stronger the acid. Okay, so let's do this another way. Okay, so I have my water molecule again. And again, you might want to put this in your notes because this is going to come up in high school for sure. So here's my negative, here's my positive. So I'm going to put, I'll put it up here, NaOH. Same thing, it's going to dissociate, it's going to break apart. Now this is different though. This is going to break into a polyatomic ion, which you have written down from your notes. There's a whole bunch of polyatomic ions. OH, or hydroxide, is just one of them. So I'm going to put OH negative and Na plus. Okay, the OH negative attaches to the positive side because it's negatively charged. And the sodium, just like salt, hooks on the positive side. If you have a hydroxide ion dissolved in water, it is a base. Now this definition becomes more complicated later. I usually go over it, but I just can't right now. A base is really anything that can, any substance that can accept a hydrogen ion. If you look at something like the chemical formula for baking soda or something, it doesn't have an OH, but baking soda can accept a hydrogen ion. So this idea is going to become more complicated for you later, but just for now, hydroxide ion dissolved in water, it's a base. Okay, so really what we have right now is, and this is in your notes, if you have a hydrogen ion dissolved in water, it's an acid. If you have a hydroxide ion dissolved in water, it is a base. And that's it. Okay, so, and the more hydrogen ions you have dissolved in the water, the stronger the acid, or the lower the pH. The more hydroxide ions dissolved in water, the stronger the base, or the higher the base. The closer it's going to be to 14. Okay, so let's look at a simple acid-base, what's called neutralization reaction. And we're going to use those two substances that we just went over because it's really easy to explain. And this is the example in your notes. I just want to go over how this works. I have HCl, and just for future reference, HCl, it sometimes says AQ. That means aqueous dissolved in water. So I have HCl, aqueous, it means HCl dissolved in water. You can't have an acid or a base without water because that's what it's used to dissolve in. So I'm going to put NaOH. There's my base, because there's my hydroxide. So AQ. Okay. Now, what's going to happen is the ions are going to switch. So you can put, and this isn't in the notes because it's hard to draw in the notes, so I would put this in there. The hydrogen ion is going to break off, the chlorine ion is going to break off. Same thing over here. The sodium ion is going to break off. And the hydroxide ion is going to break off. Remember, polyatomic ion. And they're going to flip-flop. So the positive ion here is going to now join with the negative ion there, and we're going to get NaCl, which is salt. And these two now join up, and I get HOH. Now, we usually don't write it like that. We write it like this. So when you mix an acid and a base together, oops, let me close my email real quick. Okay, so when you mix an acid and a base together, you get a salt and you get water. Now, a salt, by what I mean by that is salt is any ionic compound. Any ionic compound is a salt. So potassium chloride, that's a salt. It's ionically bonded. Magnesium oxide, ionic, metal and non-metal. That's a salt. But this is salt. Yeah, that is salt, but it's because it's ionically bonded. Remember, in science, some things means different than what you're used to. Any ionic compound is chemically called a salt. So just review, you mix an acid and a base, you get a neutralization reaction, which results in a salt and water. So let's look at this real quick. I'm going to make this a little kind of a mess here. So I've got HCl, and let's say my pH of the HCl is 0. Really strong acid. Okay, plus NaOH. That would be a pH. That means potential for hydrogen, actually. Potential for releasing a hydrogen ion. Anyway, pH of 14. Okay, so I'll put a little thing that doesn't look like an O. 0 and 14. And what I get from that is NaCl plus H2O. And the pH of these two things, it's just salt water. It's salt water. So the pH is 7, right in the middle, between 0 and 14. Okay? Now, concentration-wise, that's what I wanted to get to the electricity part for. And this is going to, man, I hope this works, and I hope it makes sense. So what I have is a little lab set up here. And I'm really hoping this works. We're going to see. Okay, so I have my light bulb here, and I have a little battery pack off to the side. Let me move some stuff around here. So what I have is a light bulb, battery pack, and some wires that are getting kind of cumbersome right now. But if I join the two ends, the light bulb lights up, right? Duh. Okay, now, if I have, this is salt water, okay? If I put these two in the salt water, the light bulb lights up. Now notice how it doesn't light up as well as that does, right? But it does indeed conduct electricity, okay? So what happens if I have just plain water? It has to be deionized water, okay? So I just happen to have some at home because this is what you put in, like irons and stuff, so that the ions in the tap water don't ruin your clothes iron. But if I do that, if I have pure water, it doesn't conduct electricity because there's no ions in there to conduct electricity. Okay, so the more ions you have, oh man, I hope this makes sense. The more ions you have dissolved in the water, the more electrically conductive it is. So no electrical conductivity, right? Super concentrated salt water, okay, conducts electricity. So what if we were to make sure you kind of keep an idea of how bright that is. Kind of hard to see from your point of view, but hopefully this, I've tried it a couple times and it works. So I'm going to take this and I'm going to dilute it. I'm going to put some just deionized water in it, make it weaker. And it's lighting up, but not as much. So the more ions it has, the more electrically conductive it is. So I'll put some even more water in there and dilute it even more. So now it's not very concentrated. And you can see it's, now I'm starting to cause a chemical reaction here. So there we go. It's lighting up, but not very much. Okay. So the more ions it has, the more electrically conductive it is. Okay, and the more hydrogen ions, this is where it all comes together. The more hydrogen ions you have, the stronger the acid. The more hydroxide ions you have, the stronger the acid. So if you have a really strong acid, it conducts electricity really well. If you have a weak acid, it doesn't conduct electricity as well. So what I have is some baking soda and water, which is a weak base. So I'm going to take my electrodes here and put it in there. Okay, and it glows pretty, it's not too bad. Okay, there we go. It's glowing, but not, it's not too great. But that makes sense because baking soda is a weak acid. Or if I take something like bleach, it's a lot brighter because bleach is a stronger base than baking soda is. And we can do the same thing with acid. I tried vinegar, but vinegar is actually too weak to conduct electricity, at least in a beaker. But what I have now is I don't have hydrochloric acid at home, obviously, but I do have rust remover, which is sulfuric acid. And I put that in there, and we got really bright because sulfuric acid is a really strong acid. Okay. Ooh, got some bubbles in there. Got a reaction going. Yeah, that's pretty cool. Okay. So that's how that works. Okay. So I hope that made sense because this is what the FET is going to be on. It's going to be about acid and base strength and how that strength affects electrical conductivity. The more ions you have, the stronger the electrical conductivity. So I have an example of the interactive notebook assignment for you that I want you to copy down. Bleach all over me. Okay. So here is the table I want you to copy down for the interactive notebook assignment. Okay, and I just realized this is almost 20 minutes long, so I'm going to try to cut it short. Sorry. So go ahead and copy that table down. Okay, go ahead and hit pause, and then I'll explain what to do in a second. Okay, there's a video down below that explains how to operate the FET, but it's pretty simple how the FET works. In water, plain water, what do the ions look like? And I'll explain what the H3O means once we get there. But really what it is, if you think of H2O, that would be neutral. But if you add another hydrogen onto it, there's your positive ion. That's your acid. So you can think about this as an acid, and then there's our base. Okay, so draw the ions. And some of these are going to be just full of ions because a strong acid's going to have a lot of ions. So I'll explain it once we get there. But ions in water, what the equation is. This means it can go back and forth. Paper color, it's going to have pH paper on there, what the pH is according to the color. And then it's also going to have some electrical conductivity part of it as well. Okay, so I'll see you over at the Fed instructions, and thanks for hanging with me for 20 minutes. Take care.